Hi and welcome everyone to part 4 of my video playlist about the best strategies for olefinating ketones. This presentation is about olefinations with geminal dihaloalkanes, with polar organometallics and with the aid of elemental titanium. Geminal dihaloalkanes are not readily available reagents, with the exception of halogenated methanes and acetic acid derivatives, which are prepared on a large scale. One way to prepare structurally more elaborate geminal dibromoalkanes is to treat aldehydes with bromine and a phosphide. Olefinations with geminal dihaloalkanes proceed by formation of either a dimetalloalkane or a carbene complex. Addition to ketones yields a beta-alkoxy organometallic intermediate which undergoes beta elimination to yield an alkene. In this example, the nucleophile was generated from methyl dichloroacetate by treatment with metallic zinc and THF in the presence of acetophenone. Zinc often requires some kind of activation to react with alkyl halides, and here chlorotrimethylsilane was used for this purpose. Dichloromethane is usually too unreactive for such one-pot olefinations, but occasionally successful examples are reported. Here, dichloromethane was metallated with a mixture of magnesium and titanium tetrachloride, and a substituted cyclohexanone could be methylated in high yield, without any modification of the methyl carboxylate. Similar conditions as those of the previous example also enabled the olefination of ketones with dichloromethoxymethane. Triethylamine was probably added to maintain a basic reaction mixture and prevent hydrolysis of the product. Carbon tetrachloride can be used to convert ketones into dichloroethylenes, as shown here. This reaction can also be accomplished with triphenylphosphine and carbon tetrachloride. The product is a carboxylic acid derivative and can sometimes be converted into an acid, an amide, or an ester by treatment with the corresponding nucleophiles. A further strategy for the preparation of alkenes from ketones is by dehydration of tertiary alcohols. This is not a very versatile strategy because in many instances regioisomeric olefins may be formed. Sometimes, however, this can be a practical approach for preparing olefins. Here, for instance, a non-enolizable ketone was converted into a mixture of isomeric olefins just by adding a Grignard reagent followed by treatment of the tertiary alcohol with hydrogen bromide. This strategy probably generates less waste and is less expensive than a classical Wittig reaction. Combinations of a bromoacetate with metallic zinc are a practical reagent for converting ketones into substituted acrylates. Even enolizable ketones can be suitable starting materials, but chloroacetates are usually too unreactive. Aldehydes and ketones can also be converted into alkenes by treatment with elemental titanium in the so-called McMurray reaction. Best results are obtained when preparing symmetric alkenes, but many successful examples have been reported of the cross-coupling of two different aldehydes or ketones. It is assumed that this reaction proceeds by an initial pinacol coupling, followed by reductive cycloreversion and formation of the alkene and titanium dioxide. If two different ketones are to be coupled, it helps if their reactivity differs significantly. Benzophenones usually dimerize only slowly and can therefore be cross-coupled with more reactive ketones, as in this example. The conditions of the McMurray reaction are mild and enable the preparation of acid or base-sensitive products. Elemental titanium is usually generated by reduction of titanium tetrachloride with its zinc and THF, often in the presence of pyridine. If sensitive alkenes are the target, then a complete reduction of the strongly acidic titanium tetrachloride is important, and pyridine may help to buffer the reaction mixture. In this example, an unreactive benzophenone was again coupled with a more reactive aliphatic ketone. Unfortunately though, large quantities of a pinacol rearrangement product resulted. In this instance, the pinacol rearrangement was particularly favored by the ability of the dimethoxybenzhidryl group to stabilize carbocations, and by the release of ring strain upon ring enlargement of the cyclobutyl group. Anyway, pyridine or a tertiary amine may have suppressed this pinacol rearrangement by keeping the mixture basic. Acetoacetates are highly enolized and generally poor electrophiles. Nevertheless, McMurray reactions seem to work even with these unreactive ketones. In this example, a cross-coupling of an unreactive benzophenone with an acetoacetate gave 40% of the target alkene. Sometimes viable yields of cross-coupled product can even result upon treating equimolar mixtures of two similar ketones with elemental titanium. In this instance, the theoretical yield is only about 25%, but a higher yield was achieved anyway. It sometimes pays to try one's luck. So what are the typical byproducts of these reactions? Polar organometallics are strong bases, and basic reaction conditions can always cause aldol condensations of enolizable ketones. Most enolizable ketones also undergo aldol condensations in the presence of acids. Thus, typical side reactions of the McMurray reaction include aldol condensations, for instance if titanium tetrachloride wasn't reduced completely. Titanium tetrachloride is a strongly acidic condensing reagent which readily mediates aldol chemistry. Polar organometallics are also strong single electron donors and can convert ketones into radical anions and then into pinacols. Pinacols are also frequently obtained as byproduct of McMurray couplings, in particular if too little titanium was used. Sterically demanding ketones do react with polar organometallics only slowly and are sometimes reduced by single electron transfer instead. This can cause the formation of alcohols or pinacols. Then, unreactive electron-rich ketones, for instance acetophenones substituted with electron-donating groups, are sometimes reduced to alkanes by elemental titanium. When using polar organometallics to olefinate ketones, the most important byproduct is the tertiary alcohol. Not all tertiary alcohols eliminate water readily, and often the alcohol will have to be isolated and dehydrated in a second step, for instance by treatment with thionyl chloride or phosphorus oxychloride and pyridine. In olefinations with geminal dihaloalkanes, one potential side reaction is the cyclopropanation of the product. Carbene complexes sometimes cyclopropanate alkenes effectively, as for instance in the Simmons-Smith reaction, where cyclopropanes result upon treating alkenes with diiodomethane and zinc. In this example, an indole was cyclopropanated during the methylation of a ketone. The fact that the newly formed alkene was not cyclopropanated indicates that the cyclopropanating reagent was electrophilic, with a preference for electron-rich double bonds. One potential intermediate of the reaction of metallated 1,1-dihaloalkanes with ketones are 2-haloalkoxides. If insufficient metallating reagent is available, or if the reaction temperature is too high, then this alkoxide will cyclize and yield an epoxide, as in this example. Then, carbene complexes may dimerize, or the dihaloalkane may act as electrophile during metallation. Therefore, homocoupling products of the dihaloalkane should also be expected as potential byproducts. The outcome of McMurray couplings depends a lot on the structure of the starting ketone. If the ketone is sterically too shielded, the initial pinacol coupling may be too slow, and secondary alcohols can result. This occurred in this example. Although with most other closely related starting materials, the main products were pinacols. Then, electron-rich acetophenones or benzophenones can also be reduced to alkanes by elemental titanium. Surprisingly, alpha-ketoamides, such as for instance isatenes or the starting material of this example, are also reduced to alkanes by titanium. The cyclized product probably resulted from an intramolecular Claisen-type condensation of the phenylacetamide. Organotitanium intermediates can sometimes olefinate carboxylic esters, as in this example. Thus, for starting materials with both keto and ester groups, a careful optimization of the amount of titanium may be required. Here are some more examples to give you an idea on the scope of these reactions. You can also find this reference list in the description of this video. This was my last video about the olefination of ketones. Hope you found it useful. On my channel there are also 4 videos about the olefination of aldehydes for further inspiration.